Good afternoon. My name is Rob Muiller. I'm a senior technologist and co-founder of the SwampWorks, which is an innovation environment at the Kennedy Space Center. I'd like to acknowledge my co-authors, Dr. Tracy Prater, a materials engineer at the NASA Marshall Space Flight Center. Monsi Roman, who's a program manager for the Centennial Challenges program, and Tony Kim, who is the deputy program manager also at Marshall Space Flight Center. There's been a long history of prizes throughout human history, and they've been shown to be very successful. First one that was really extremely successful was the Longitude Prize. And this is to do with navigation on the high seas. It was possible to measure latitude, but not longitude, so the British Empire commissioned a prize for the first entity, individual, company, university to come up with a solution for how to measure longitude. And eventually that was won by an individual who invented a maritime chronometer, and then the time difference between Greenwich Mean Time and the local time was established, and then tables were used from existing star charts to calculate the longitude, which opened up the high seas for navigation. But one thing I want to point out to you is it took 51 years to achieve that prize. And now it's a long story. If you want to read about it, there's several books that have been published about that story in television programs. It's an intriguing story, but it took quite a while. And that's one of the conclusions, is that these prizes do take some time. Next one is the Orteig Prize, which was won by Lindenberg in the spirit of St. Louis, first person to cross the Atlantic without stopping in an airplane. And that was achieved, and it did open up a whole new era of aviation, and very successful. So another example of a successful prize. The Ansari Prize, also successful, and established a new way of reaching the 100 kilometer boundary of space, which is an artificial line we draw. Also, if you notice, there's 8 years for those two prizes, so it takes time for these prizes. And the Google Lunar X Prize was never claimed, and they ended up canceling it. So these are not easy, these prizes, and they shouldn't be easy. In the spirit of these competitions, NASA has been authorized by the US Congress in 2005 to establish a series of competitions called the Centennial Challenges. And so NASA has had many Centennial Challenges over the last 10, 12 years. The latest one is a 3D printed habitat competition. And the idea is that we will not take the materials with us in the same spirit as the last presentation. I don't think we will be launching concrete and steel I-beams or aluminum feedstock into space to create habitats on Mars. I just don't think the gear ratio, which is 11:1, so for every kilogram you launch to low Earth orbit, or for every kilogram you land on Mars, you have to launch 11 kilograms to low Earth orbit. That gear ratio is prohibitive, cost prohibitive, logistics prohibitive. It's just not the right way to do it. So we think that if you use the local materials on a planet, moon, or asteroid, you can create habitation. So also, the world's population is increasing. Between now and 2100, 47% increase is projected. So we need affordable, sustainable housing and shelter in general here on Earth. It requires aggressive construction practices to satisfy the increased demand. So how are we going to do this? We think that if we have a prize for a space habitat, this will get a lot of attention, and we can then use the same technologies on Earth to create economic benefit and social benefit. This is not a dream. We're already doing it today. This is an example of a project that NASA had with the US Army Corps of Engineers of printing a shelter for the soldiers. We call these B huts. B stands for barracks. It's 32 feet long by 16 feet wide by 8.5 feet tall. Sorry, it's in English units. You can do the conversion. And the point is these walls are printed a little bit non-conventionally, so it shows the promise of 3D printing is you can do non-conventional shapes. And so basically 3D printing, additive manufacturing, we call this actually 3D automated additive construction. So there's still some debate on what this field should be called, but in effect it's automated construction. We use Portland cement, concrete here, because the Army thinks they can get it anywhere in the world, which is true. You can buy Portland cement anywhere in the world, and they don't want to be constrained by logistics. But the aggregate you could find locally, and so that would reduce the logistics for the military. It removes design constraints, so manufacturing for design. When you design these structures, you have to think about the manufacturing. That's the whole point. Enables building and testing earlier in the project life cycle, ability to work with new material formulations, maximize use of in situ resources. These are all the things we're trying to achieve. Now, very quickly, I'll give you a quick 30-second tutorial on what the state of the art is. State of the art in additive construction is basically, there may be others too, but these are the two main ones, it's either a Cartesian coordinates XYZ platform, a large version of your desktop 3D printer, which is XYZ, Cartesian coordinates, and then a slurry is extruded out through a nozzle and additively using additive construction. So the Army, for example, is using this Portland cement slurry, but there are also extrusion of wire filaments, either metallic or polymer based or polymer concretes. So there's a variety of different materials being developed. And then the other style of construction is this robotic 6 degrees of freedom, sometimes more than 6 degrees of freedom, robotic arms. And there's a picture of Ranch Technologies who's doing this kind of construction. Now here's why I think this is a very good solution. If you go to the moon today, it's covered in aggregate. It's not really an exotic material, it's crushed rock. We know what it is. Been many studies on this. In the Mare, it's basaltic. In the highlands, it's anorthite and other minerals. But we largely know the geology of the moon. We have a big advantage. Over 4.5 billion years, Mother Nature has pounded the moon and other planetary bodies, asteroids, and created a fine dust that covers the top 8 to 10 meters of our moon are covered in this fine dust. The dust is between 20 and 100 microns in size. It's crushed rock. It's a great aggregate. So that's a lot of energy that we don't have to use to crush the rock. So we have aggregate. Then what we'd like to do is apply new technology, new materials to this aggregate and have autonomous systems that can then 3D print shelter. As a benefit, we could have affordable global housing, and the military is interested in using this as well. The competition itself had 3 phases. I reported last year in Australia at the IAC about phase 2, which is a structural member. Phase 1 was for architects. This was more of an architectural competition to come up with new ideas on the design. That was awarded to the Mars Icehouse team. And last year, Branch Technologies won the materials part, and this year we have the on-site habitat. Now notice the prize purse is very small at the beginning, but now it's growing, and this year we have a $2 million prize purse. Now this doesn't happen by itself. It requires what I call a coalition of the willing. And so we assembled a group of interested parties. You can see the Centennial Challenge program provides the prize money. U.S. Army Corps of Engineers is providing technical advice. The American Concrete Institute is very interested in spreading the information to their members. Caterpillar is our main sponsor. They provide the site, the test site, and some other budgets to run the competition. Bechtel is also involved providing technical expertise, and Brick and Mortar Ventures is a Silicon Valley outfit that hopes to invest in this one day. You can see that this is competition has been happening already since 2015. We're now in 2018. We're in phase 3. Construction level 2 is next. Deadline December 5th. phase 3, we have another thing we said is not everybody can afford to build a 3D printer and bring it to Peoria and print a house. So let's have a virtual construction for the universities, for the living room scientists and engineers, for the people who can't afford to 3D print. Let's have a virtual construction competition. We did that, and also including BIM, Building Information Modeling, is very sophisticated. You can model all the functions of a habitat with BIM now. So we'll have the level 2 January 16th, then in April 29th to May 4th, we'll have the on-site competition, Peoria, Illinois, head-to-head. 8 teams will show up and do an actual construction of a habitat. This is a picture of the phase 2, and this was actually spectacular because this material is a polymer concrete. It's actually basalt glass with PET, thermoplastic, extruded out of a nozzle. But that top piece is very difficult to do. You have to go horizontally sideways, and there's very few 3D printers today that can do that without supports. This was able to do it with no supports. It builds a little spider web across the top and then uses that as a bridge to build on top of that. So it was very, very exciting work, and we were very impressed. Then, of course, we've crushed it.
2 minutes, Ron.
If you build something, you have to crush it to find out if it works. We crushed it, and this was the results. 2 teams were able to place, and Penn State and Branch Technology and Foster Partners were the architects. And now in phase 3, we asked the teams to build a foundation. Then we asked them to build a cylinder, and we fill it with water to test the hydrostatic pressure to make sure it can take pressure, because in space these will be pressure vessels. These will not be just like on Earth, compression structures. Then construction level 3 is 1 to 3 scale habitat printing. Materials is a big part of this. Fortunately, we know the materials, and these materials are ubiquitous in the solar system, including here on Earth. And basalt is one of the main materials of choice. To make it relevant, we had a challenge: how do you score the materials? If we open it up to any material, how do you score them? So we have a sliding scale, and we assign 3D factors, 3D printing factors. If you're more relevant, you get higher points. If you're less relevant, you get lower points. It's a scale with a factor, then you put the factor in the equation, you multiply it. This is the most recent result, is the printing of a foundation. Then we asked them to drop a standard Olympic shot put from a certain height to see if it's strong enough. Yes, the team did a good job. Team Search Plus is the architects, and APISCore are the engineers. This is usually the way it works. And they have this robot that you see on the bottom right. You can find it online. Printed a very nice foundation. But they did use a Portland cement concrete, so their points go down. But the construction was very good.
It's time up.
Okay, there's a picture of the tank. And here's the virtual construction level, which is coming up. You can find all this online. These are the pictures of the winners. We're going to meet at the head-to-head competition Caterpillar, and these are the prizes. And you're invited to join us in Peoria at the Caterpillar facility to see how these teams do. Thanks for your attention.
So I think we have time for one quick question. Okay.
It's a simple question. We are invited, but we have to find an American to make a team, right? If I'm not wrong.
You can participate as an international competitor.
Yeah.
But you will not be eligible for prize money, just prestige.
You're not invited.
We have laws preventing us from giving U.S. taxpayer money to international entities because it's taxpayer money. So we cannot give the prize money. But you could form a U.S. company and have an American in charge. So there are ways around it. But that's
what I heard. Yeah.
Great question. Okay, thanks again, Ron.
Thank you. Okay, so our next presenter, Barbara Inhofe, she is a reporter and very well known space architect who is doing that. And well, basically the floor is yours.
Good afternoon. It's great to see so many people here. If you don't want to stand in the back, you can sit in the front on the floor, that's not a problem, or take a chair from somewhere else. The presentation or the project I'm presenting is called Regolite. It's using solar sintering to build infrastructure on the moon, and it's the latest advancement in that project. The project is a collaborative project under the lead of the German Aerospace Center in Cologne. And we had as partners Space Application Services from Belgium, COMEX from France, and Bollinger Kroman from Vienna Structural Engineering Office. And then, of course, LIQUIFER Systems Group. The project was a Horizon 2020 EU funded project. Okay, what is solar sintering? It is using the sand, in our case on the moon, and the sun, and only these two components to create elements, building elements, just without these two elements, and for why? To build habitats, shelters, terrain for telescopes, or for launch pads. It's an additive layer manufacturing process, so your sintering is not melting, it's before melting, it's kind of gluing layers of sand together. We started off the project with a TRL3, it's a proof of concept basically, and advanced it to technology readiness level of 5. That is proving that the technology works in a relevant environment. We did 3 printing campaigns for this, and one of the near TRL5 which we could reach was a printing campaign in a vacuum chamber. So this was the first printing campaign in the ambient conditions. It was an automated XYZ table fed by a computer by a geometry which we as architects developed. And you could see the solar ray hitting the moving table. The German Aerospace Center has provided these facilities with infrastructure and the printers basically made by Space Application Services. And the DLR are experts in granular matter, and we were using the JC2A simulated or simulation sand, which is a basaltic sand from the Mars area, or simulation, a representative of the Mars area on the lunar surface. On the right hand side you can see the final sintered element. And also just look closely that there's a little bit of bending, and you can still see some layers that talk about this a little bit later. The second printing campaign was with a so-called mobile printer. It's slightly different. The table is stable, and the mirror, the Fresnel lens, actually moves, and it's meant to be representative of be built or be mounted on a moving object, on a rover on the moon. And it was operated during sunlight in Belgium, imagine. The third and last printing campaign was in a vacuum chamber. The vacuum chamber was quite small, but it was a similar setup as in the ambient conditions. And it was also a fully automated process. So what we're trying to do is, for these different printing campaigns, to develop a wide range of interlocking elements and 3D, different kinds of 3D geometries, ranging from elements with 3-dimensional interlocking capacities, or tooth elements, or randomly packed aggregates. These, for example, could be imagined to be part of a launch apron, like just assembling, taking all the dust from the launches, or the ascents or descents. Reciprocal elements, cobalt wall structures would have been another solution. and then elements with two-dimensional interlocking capabilities and flat ground stabilizing elements. So a whole catalog was produced for this. And it's just to show that what the possibilities are. In the end, actually, we were coming up with the dodecahedron elements because they are compact. They work in all different directions, X, Y, Z equally, and are interlocking. So that is something which was found also from the perspective of being not having sharp angles. They were quite useful actually to, in the end, to work with them or to design the scenarios with them. So at one hand we created all these technology tests, the printing campaigns, and on the other hand we were looking, okay, where do we want to apply them and how? The facts and the findings, we did come to a resolution of printing to merely 10 millimeters. We found it, well, but you cannot print sharp edges. You see that on these parts here, that there's all, they're all rounded off. There's still, in the next phase, we'd like to look into the delamination, because it's still, some pieces got, were sintered really well, some were not. So we still have to work on the how we create the optimal layer thickness and optimize the temperature. And also the warping is an issue that has to do with the plate and the temperature, so the ground plate where things set on. We could reach right now mechanical properties of gypsum, but we anticipate that we could come close to concrete. If we are not using reinforced concrete, we could, there's Hannah Lack actually in the next presentation will talk about reinforcement, or that's how fibers, which could be used potentially as reinforcement, as I see it. But as long as we don't have that, we have to look at catenary curve-based structural geometries, which you can see here. And then, of course, in the end, the larger an interlocking element is, the less important is the resolution. So, to the conclusions, it was quite important to have all these different tests, and for us as architects being mostly involved in the design of the geometry and the scenarios, and also for designing the specific elements to be printed. We found out, or the recommendations we would give is using solar sintering. We would design with elements with obtuse angles, with a compact geometry. This is actually what the dodecahedron is offering. And then the elements should be as big as possible. With the mobile printer, we could reach a building volume of 50 centimeters width, 50 centimeters height, and 1 meter depth. So that is quite a useful volume. And then we could also imagine to have a survey process in parallel to the building process. This is a little animation which summarizes the geometries being developed and how the dodecahedron is actually developed from an original tetrahedron. I don't know if I can speed it up a little bit. So here you see how these all these flexible and reusable, and then the first layer, which gives you a structural integrity, and then you can put sand for radiation shielding, and then just a structural rigidity parts of it covered again to reach the thickness, the 2 to 3 meter thickness you need for radiation protection. So you can imagine that together creating from these different elements with inflatable structures a lunar base that this could look like this. But not only pressurized shelters are important, because you might also want to protect some of the machinery in non-pressurized shelters. And finally, you of course can also shape a launch pad and probably a crater. You can design it such, or you can use these elements, sintered elements, to have a telescope. This concludes the presentation.
Time for a question? Over here.
When I just saw the name, it looks like it was a huge team, collaboration, a huge team working on it. And I got the impression that space architecture is very relatively easy, that anyone can do it. And it doesn't require so much expertise. Can you just tell us what kind of disciplines that have been involved in this, just to understand how difficult it is?
Wow, Martin, that is quite a question. Well, first, the space projects are always interdisciplinary, so it just depends on how wide you stretch the disciplines. And with this project, I think it was quite essential to create these different geometries, because otherwise the scientists, so we had scientists, engineers, and architects, and scientists and engineers of quite a diverse variety, roboticists and structural engineers. And so if the scientists, they were interested in the granular matter. So they look always into these, the sand and how it behaves and so on, and they, this is enough for them. But then, you have to always contextualize, because this is not only fundamental research, but it's also technology development. At the same time, you also have to show, and you have to integrate from the beginning what you actually do with it in the end. You have to contextualize. And I think that is one of the most important parts that where architects can contribute to, because they're integrators, and they always design from the big picture to the detail and the other way around. So I think that is that I would say that's what we brought to the table. I mean, we created the scenarios and these different geometries, which were then put to test in the printing campaigns with various outcomes. It's a really how can I say, well, probably we were all hoping for that finally we have this big element being printed, but it's not that easy. And the people who try to implement something in the space business, they know this.
So it looks like the 3D printing is not very precise, so your shapes are kind of quite forgiving to put them together into a shape. Do you glue them together, or they just self-stick together?
They self-stick together. They self-stick together, and I think that's Thibaut, you got a good point, because that is actually it was quite a long process. That's to Hartem again to actually come up with a geometry which is forgiving, which fits to that kind of printing process, and then which you don't have to glue, because we don't want to use additional material. I think the most convincing part in solar sintering is that that you don't need any binder. You have the sun in abundance on the moon, and the sand in equally abundant. So I think this is the most convincing part here.
Okay.
Quickly, one more.
I understand you've been focusing on lunar regolith. How much work have you been doing on the side, thinking about other materials? Let's say there was some other planet with maybe a lot more iron in the regolith than we wanted to build on. Would you have to start from scratch, or could some of the technology be repurposed?
I don't know if there's any technology. I mean, this project was really about advancing the solar sintering in a concurrent design approach. But I wouldn't know. I don't know, Brent, if you know of any other. I mean, there are various studies, but if there's a kind of technology which has been tested for building, you mean? Or for
I'm thinking about
just resources.
stuff.
I think your question can be answered by
Microwave sintering is a candidate, especially if you have iron. On the moon, if you have nanophase iron, it helps with microwaving. On Mars, if you have iron, it also helps. So I would say my answer is microwave sintering is the next obvious candidate if you have a lot of iron.
And my answer would be there's not that many other planets. All right, so we're going to need to move on.
Thank you.
Thank you again, Barbara.